Hi guys, this is Dr. K. This is a short tutorial on using the reaction quotient. It uses slides and data that are actually from the lecture. I do present it in a slightly different way, so I hope this is useful to you. First, a couple introductory ideas. First of all, the reaction quotient has exactly the same format as the equilibrium constant. The only difference is you're using the reaction quotient not to calculate the equilibrium constant, but calculate the quotient to see whether or not a reaction is at equilibrium. You'll know a reaction is at equilibrium when the reaction quotient and the equilibrium constant are the same numeric value. Now, if the reaction is not at equilibrium, you'll know that too, because it won't be the same value. But what the reaction quotient allows us to do is it allows us to figure out what direction the reaction has to shift in order to get the reaction back to equilibrium. That's an important concept in these problems because a lot of times you're given concentrations, you're not told what direction the reaction needs to shift, and you need to get those signs correct when we do the ice tables in order to get the right answers for the problem. Okay, so here's the problem. Question is simply, is this reaction at equilibrium? And then you're given some data. One of the first things that I like to do when I'm given the data is I like to write the numbers in right underneath the problem. So this is 0.0402. This is 0.1207. And then the NH3 concentration is 0.00272. This helps me avoid some mix-ups that usually happen when you just try to read the numbers out of the problem. And those mix-ups are really just a transposition of the numbers for the different substances, the reactants, and the products. The next thing to do is write out Q. And Q, again, it has the same form as equilibrium constant. It's products over reactants. So in this particular instance, it would be the concentration of NH3 squared divided by the concentration of N2 times the concentration of H2 to the third power. The next step is just to plug the numbers in. Q is equal to, and we can read right from these numbers that we wrote over here, NH3 is going to be 0.00272 squared divided by 0.0402, extend this line out, times 0.1207 cubed. I'll run this through my calculator real quick, and what I find is that the value I get for the reaction quotient is 0.1046. Again, keeping track of sig figs, that means that Q is equal to K, and so this reaction is at equilibrium. The next part actually says what happens if you reduce the volume of the container by half. So just a little side note here. So when you decrease the volume by half, then what you end up doing is doubling the concentrations of each substance. So if you assume, think about this, if the reaction doesn't shift, you have the same number of moles in the container and the volume is decreased by halves, the moles per liter will have to have doubled. So here's what we have. We have reducing the volume by half causes the concentrations to double, and these are the concentrations that you have. So the question is, which way is the reaction going to shift? Now I'll show you later, there's a concept called Le Chatelier's principle, and Le Chatelier's principle actually allows us to predict the direction of the shift without having to calculate Q. But in this case, let's calculate Q, since we haven't covered that yet. Q is equal to, and again, it's products over reactants, so following from the previous slide, 0.00544 squared divided by, so the concentration at N2, which is 0.0804, times the concentration of H2 cubed, 0.2414 cubed. So I run this into my calculator, and what I get is that Q comes out to be 0.261. So let's flip back really quick. And you can see the equilibrium constant is 0.105. So Q is less than K. That is 0.261 is less than 0.105. So what does that mean? Well, remember, Q is the ratio of products over reactants. In order for the reaction to get to equilibrium, we're going to have to take some reactant and convert it over to product. That does two things. It makes the product side go up, so Q gets closer to K, and it makes the reactant side go down at the same time. So when we set up our ice table, which we'll do in the next slide, we have to say then the sign for the changes in the reactants is going to be negative, and the sign for the change in the products is going to be positive. So let's work that problem out. So setting up the ice table, we're going to start with the concentrations of reactants and products and the balanced chemical equation. And what I'll do is I'll do what I normally like to do. I'll take these concentrations and I will write them right underneath the reaction, and I set up my ice table just like this: initial, change, equilibrium. Try to draw straight lines on here. It's not very easy, but N2 is 0.0804, H2 is 0.2414, and NH3 is 0.00544. And I do like to put a double line down the middle here so that I can keep track of reactants and products. So now we decided that the reaction, in order to get to equilibrium, needs to go from the left to the right. So we know the signs on the left are going to be negative, the signs on the right are going to be positive. The change for N2 is just going to be minus x, and H2 is going to be minus 3x, and NH3 is going to be plus 2x. So what I know is at equilibrium that the following equations are representative of the equilibrium concentrations. Remember, you just take the top box, add it to the change box, and set it equal, and add those together, and those equal the equilibrium box. So now 0.2414 minus 3x and 0.00544 plus 2x. On a problem on an exam, this is actually what I want you to see you do, is make sure that you set these boxes up correctly, and then you can write that K is going to be equal to, again, it's the ratio of products and reactants, but it's going to be 0.00544 plus 2x squared divided by 0.0804 minus x times 0.2414 minus 3x, that whole quantity cubed, and to get this thing to equilibrium, we set it equal to the equilibrium constant, 0.105. So what we have is that I plug it into my solver, and it tells me that x is equal to 0.002425. Now, I can plug those in real quick, but before we do that, let's think about this particular solution to the equation. X has to be greater than 0, so x is greater than 0. But we also know it has to be lower than what we call the upper bound in this problem. Now, in class, what I've been showing you is that you can, in fact, determine what the upper bound is by looking at these values to determine which one gives you the smaller x value. As it turns out, the upper bound is 0.0804, and in fact, that answer is well below the upper bound. Now, having said that, the other way you could check the upper bound, that is, once you see that your answer is positive, that's good. The other way you can check your upper bound is simply by plugging x into each one of these expressions. So let me go ahead and do that. So I'm going to take 0.0804 and subtract x from it, and I get that the concentration of N2 is 0.07798 with 3 sig figs. On the H2, I can get 0.2414 minus 3x, and I find that the concentration at H2 is 0.234. I'll carry one more digit in my calculations, and that the concentration at NH3 is 0.00544 plus 2x, and that gives me a value of 0.01029. So none of those values are negative, which indicates that my upper bound is good. So those are my concentrations for this problem, but let's say you're not certain and you want to check to make sure you got the right answer. The appropriate thing to do at this point is actually recalculate the value for Q with the values that you calculated using your solver. So Q is going to be the concentration of NH3 squared, so that's 0.01029 squared, and then divided by 0.07798 times 0.2341 cubed. So when I do that, what I end up finding is that Q that I calculate is 0.1058, or rounding 0.106. Within the significant figures on this problem, that's close enough to KC to say that we probably did our calculations correctly, and that the calculations at equilibrium are these values that we calculated up here. Alright, I hope that helps you. If you have any questions, feel free to email me or ask me in class.